Oregon's committee materials describe data center water cases across Hillsboro, Prineville, the Dalles, Hermiston, Umatilla, and the Port of Morrow. Local records exist, but they measure different things. In March 2026, a draft prepared for the Governor's Data Center Advisory Committee said there was no aggregate data on data center water use in Oregon. That finding did not erase the local figures, it exposed the fact that they did not describe the same thing. One city reported data centers as a percentage of its total supply, another treated water volumes as trade secrets, one company reported annual water use, a planning document recorded reserved capacity, a different project transferred water rights and funded storage. Each figure can be accurate and still fail to answer the public question. AWS also presented a 2024 Oregon total of 284 million gallons, but the three visible components on its slide add to 243 million. The missing 41 million remains unresolved in the public record reviewed here. How can Oregon decide what data center water costs when the public numbers do not measure the same thing? The investigation begins inside the cooling system. Water can be withdrawn, circulated, evaporated, discharged, reused, or counted indirectly through electricity. A statewide total explains little until those paths are separated. Water reporting sounds simpler than electricity. A pipe has a meter. Read it, add the gallons, and compare the result. That works only if every meter is measuring the same boundary. A withdrawal is water taken from a river, aquifer, reservoir, or municipal system. Consumption is the portion not returned to the same local water system in a useful form, often because it evaporates. Discharge is water released after use, potentially through a sewer, treatment plant, land application, or permitted outfall. Return flow can remain available downstream even though its temperature or chemistry has changed. Capacity is different again. A city may reserve enough pipes, pumps, storage, or water rights to serve a future peak. That is a commitment in the system plan, not proof that a facility used that amount last year. Then there is timing. An annual total can hide a demand concentrated in the hottest weeks when river flow is lower, farms are irrigating, and households are also using more water. A modest yearly share can still matter if it arrives on the system's hardest day. The draft also asked about indirect water use from electricity, which depends on the generators, time, geography, and accounting method. That modeled footprint cannot be added casually to a city meter. The larger data gap comes from incompatible boundaries. A company may combine several Oregon campuses while a utility records only the meters in its service area. Units answer different questions too. Annual gallons describe volume, daily gallons describe flow, percentages describe a share, and water use effectiveness relates consumption to computing energy. A campus can improve efficiency while using more total water if it grows, and a modest annual volume can still require large pumps when most demand arrives during 10 hot weeks. Those boundaries change the public answer. Withdrawal shows what leaves the source, consumption estimates what does not return locally, and discharge shows where used water goes next. Reserve capacity can force a utility to build pipes and storage even when the meter records less flow. A comparable ledger needs all four before it can tell residents what the campus requires from their system. A data center campus has to move server heat outside continuously. Fans or liquid loops carry it from processors to pumps, heat exchangers, and mechanical equipment, which finally reject it to outdoor air. There are several ways to do that. Dry coolers move heat through coils without evaporating water in the final step, but fans and compressors can require more electricity in hot weather. Evaporative systems use water to carry heat away as vapor. The remaining water recirculates until minerals concentrate and part is removed as blowdown for appropriate treatment or discharge. Liquid cooling brings fluid closer to the chips, improving the first part of the heat path without determining the final water footprint. The heat still reaches an outdoor, dry, evaporative, or hybrid system. A hybrid plant can use outside air most of the year and water during a small number of hot hours, producing a low annual total with a sharp summer peak. The whole path matters. Electrical energy enters a processor and leaves largely as heat. A coolant loop carries that heat to a heat exchanger, another loop or airstream carries it toward the mechanical yard, and the final equipment rejects it outside. Water becomes consumptive only where the design allows evaporation or another loss, so a rack-level photograph cannot establish the campus total. The official Oregon session summary listed these families as general technology. It did not establish the exact cooling design at every named site. That boundary matters. A photograph of a cooling tower does not prove that a nearby campus uses one, and a company-wide efficiency claim does not identify the plumbing at a specific building. Each site still raises the same physical questions. What enters? What evaporates or returns? Where is water discharged and when does demand peak? Dry cooling can save water at the campus while using more electricity on the hottest afternoon. Evaporative cooling may use less electricity while consuming water locally. Oregon's draft treated indirect power sector water as an open policy question, not a settled statewide calculation. The useful design depends on which resource is constrained and who carries the consequence. Oregon has major rivers, but summer availability is local. A statewide map does not show which rights, storage systems, aquifers, or treatment plants can serve a new load. The Oregon Water Resources Department told the committee that most streams and rivers are fully allocated during summer. New summer surface water rights are generally difficult to obtain, especially in eastern Oregon. Existing municipal rights, stored water, groundwater, and transfers operate under different legal and physical conditions. Summer is also when cooling can become most demanding. Outdoor air is warmer. Evaporative systems may run more. Dry systems may consume more electricity. Rivers can be lower and warmer, while fish need adequate flow and cool habitats. Farms and cities are near their seasonal peaks. This does not prove that every data center competes directly with a farmer or a fish. Municipal systems can have senior rights, storage, treatment capacity, and planned reserves. A gallon used by an industrial customer may be drawn under a city right rather than a new site-specific right. It does mean location and timing are part of the quantity. 1 million gallons in a cool, wet month is not physically identical to 1 million gallons during a constrained summer week. A statewide annual number would need enough detail to preserve that difference. The wastewater side has the same local character. Oregon's Department of Environmental Quality explained that cooling water can pick up treatment chemicals, heat, and dissolved material. A facility may need coordination with the municipal treatment plant, an industrial pretreatment program, a surface discharge permit, or a land discharge permit. There is no single disposal path that can be assumed for every campus. The public policy problem is therefore not only how many gallons, it is whether the source, season, treatment system, and return path can support the demand without transferring an unseen cost to other users. Hillsboro offers one of the clearest local snapshots. In its March 2026 presentation, the city reported 18 co-located data centers concentrated in roughly 335 acres of planned industrial land. In its March 2026 presentation, Hillsboro reported data centers at 1.76% of its water supply and 3% of industrial water use. Those figures challenge the assumption that the buildings must dominate the municipal system simply because they are physically large. But the same presentation shows why percentages need context. Hillsboro has an unusually large industrial base. About half of its water supply serves industry. A small share of a large industrial system is different from the same percentage in a small rural utility. The city also participates in the Willamette Water Supply Program. The regional system was presented with an initial capacity of 60 million gallons per day and an eventual build-out of 120 million. Hillsboro's shares were listed as 15 million and 36.2 million gallons per day. Those are planning capacities, not data center consumption. The city explicitly said the project was not built only for data centers. It supports a growing community and a broad customer base. That is the fair reading of the Hillsboro case. The city can point to measured shares, diversified industry, and planned supply. Critics can still ask about peak demand, conservation, wastewater, and how future campuses change the denominator. Both questions require the same thing: comparable reporting over time. A percentage from 1 year is useful evidence. It is not a permanent exemption from scrutiny, and it is not evidence that every Oregon city has the same margin. The Dalles presents a different model. Municipal officials told the advisory committee that agreements in 2015 and 2021 placed specified pipeline, well, reservoir, pump station, and distribution upgrades on the data center owner or developers. That structure addresses one version of who pays. If a large customer requires a bigger pipe or a new pump, the customer funds the identified work instead of placing the entire cost on existing water users. The city said data center revenue helped make the 2025 water rate increase 7% rather than a projected 35%. The claim appears in the official facilitator summary, not an independent rate study in this source packet. Yet the same discussion exposed a trust problem. Water quantities associated with the data center were treated as trade secrets and redacted. Participants said the secrecy created skepticism. The conflict is not simply transparency versus privacy. An operator may consider process details, expansion plans, or contract terms commercially sensitive. A city may be bound by an agreement, but residents cannot evaluate total demand, drought exposure, or the value of infrastructure contributions without some consistent public measure. Google's presentation said the company invested about $28 million in water infrastructure and transferred more than 100 million gallons of annual groundwater rights to the city without cost. Those are company disclosures placed in an official meeting record. Water rights and system capacity are not the same as annual consumption, and the executed transactions need to remain distinct from the company's description of their benefit. The Dalles separates infrastructure investment from disclosure. A project can fund public assets while the core use figure remains hidden. Residents still need enough information to test both sides of the bargain. Infrastructure contributions also need a time horizon. A new well or reservoir can serve the community for decades while creating operating, treatment, and replacement costs after the original payment. Additional industrial revenue can spread fixed costs, but the result depends on the customer remaining and its rate covering ordinary service plus peak capacity. Those questions do not negate the city's 7% versus 35% comparison. They determine whether the benefit lasts. A useful agreement therefore separates the construction payment from the continuing obligation. It identifies who owns the asset, who operates it, which customers receive the capacity, and what happens when pumps or treatment equipment need replacement. That is the water system version of the episode's Who Pays question. Amazon Web Services gave the committee a statewide number, 284 million gallons of Oregon water use in 2024. On the same slide, the company listed 59 million gallons from the city of Umatilla, 136 million from the Port of Morrow, and 48 million from Hermiston and Regional Water Systems. Those three figures total 243 million gallons. The remaining 41 million is not explained on the displayed slide. It may involve another site, another supplier, or a category not shown. The public record in this research does not resolve it, so the film cannot repair the arithmetic on the company's behalf. This is a small example of the statewide problem. Even when a company volunteers a total, the viewer still needs the site boundary, source, definition, and reconciliation. AWS also said a fully developed campus using its latest design consumes about 22 million gallons per year. The official summary recorded a claim that the company uses outside air for most of the year and needs water for cooling only about 7% of the year in Oregon. These are company statements, not meter records for every campus. They do reveal the shape of the system. Water use can be highly seasonal. A campus can have a low annual water use effectiveness while concentrating most demand between June and August. Water use effectiveness, or WUE, divides water consumed by the energy used by information technology equipment. It can help compare designs when the boundaries are consistent. It does not tell a city whether a hot day exceeds a pump, treatment, or water right constraint. It also does not include every offsite effect. The 284 million gallon claim should remain labeled as an AWS disclosure. Its visible 41 million gallon gap has to remain open until a comparable public dataset reconciles it. The gap also shows why annual company reporting and utility reporting need a shared boundary. A company can include several campuses, suppliers, or operational categories. A utility sees only the meters inside its service area. Both records can be internally valid while their subtotals fail to reconcile on a public slide. Monthly reporting would add another missing dimension. The official summary records AWS saying most Oregon water use occurred in summer. If a campus uses little water through cool months and then increases evaporative cooling during heat, the annual total hides the period when the municipal system carries its largest flow. The relevant comparison is not only year against year, it is the campus peak against the utility's available summer capacity. Water use effectiveness adds design context by relating consumed water to information technology energy. It can show that one cooling design uses less water per unit of computing. It cannot reveal whether a particular city has enough water on its peak day, and a lower WUE can coexist with higher total use if the campus becomes much larger. Hermiston's public explanation shows how a project could change timing rather than simply add supply. The city of Hermiston says its 25-year water service agreement with AWS describes storing Columbia River water underground during lower demand months, roughly October through March, then recovering it for summer use. The city says AWS is responsible for construction costs. This is aquifer storage and recovery. Water is treated, injected into a suitable underground formation, held, and pumped back later. The approach can shift some withdrawal away from the season when river and municipal demand are highest. It is not free water. Pumps use energy. The geology, water quality, recovery efficiency, permits, and operating rules matter. Stored water must come from a lawful source, and not every gallon injected necessarily returns on demand. The city says the agreement is intended to serve broader community needs, not only data centers. That projected benefit has to be measured after construction and operation. Prineville illustrates another kind of planning number. A 2024 methodology report described in the research record lists reserved water capacity agreements with data centers totaling 4.658 million gallons per day. It says 1.847 million gallons per day was included in the daily demand calculation. Reserved capacity protects a future claim on pipes and supply, affecting what the city builds even when the full amount is not flowing. The 4.658 million gallon figure is reported planning capacity, not actual consumption. Together, Hermiston and Prineville show what public reporting has to separate: actual flow, reserve capacity, who paid, and whether the system performs as promised. Storage is valuable only if the city can inject water when supply is available and recover it when demand peaks. This is where an annual public report can be more useful than a one-time permit. It can show whether the system operated as promised through an actual summer, not only whether the original engineering plan looked plausible. The consequences can extend beyond a municipal meter. An annual number can miss the exact week when a river is warm, stream flow is low, and cooling demand is high. It can also miss the hydrologic connection between a groundwater source and a nearby stream. Those are the reasons tribal and fish representatives asked about source, season, return flow, and low flow conditions rather than only a statewide sum. The Columbia River Intertribal Fish Commission told Oregon's committee to ask about the water source, its connection to streams, withdrawal quantity, return flow, low flow conditions, discharge chemicals, spill planning, tribal rights, and in-stream flows. Representatives connected water and energy decisions to salmon, first foods, and treaty rights. The later May summary recorded similar concerns from the Confederated Tribes of the Umatilla Indian Reservation and Crit FC about sovereignty, water, fish protection, and peak electricity demand. These are institutional concerns in an advisory process. The records reviewed here do not prove that a named data center caused a specific injury to a named fish population, aquifer, or tribe. That claim would require site-level hydrology, permits, monitoring, and causation evidence. The concerns still identify what a complete ledger would need. A city meter can show delivery without showing whether groundwater pumping is connected to a stream. An annual total can show volume without showing the low flow week. A discharge permit can set limits without resolving cumulative demand across several facilities. Who carries the consequence depends on which part of the system is constrained. Existing utility customers may pay for excess capacity or treatment if contracts do not cover it. Farmers and fish may experience a seasonal shortage that disappears in an annual average. Tribes may face decisions affecting resources protected by treaties without receiving timely project information. A data center operator may pay millions for infrastructure and still face public opposition because the accounting boundary remains too narrow. A better record would distinguish those impacts instead of assigning every concern to every campus. The March dialogue draft listed possible directions for discussion, including better reporting, citing where supply and wastewater capacity are adequate, performance requirements, municipal forecasting, mitigation, and community water benefits. These were options, not adopted Oregon policy. A usable public ledger starts with common definitions. For each facility or reporting boundary, it should show the source, monthly withdrawal, estimated consumption, discharge or return volume, wastewater destination, peak day demand, reserved capacity, and calculation method. It should separate potable from reclaimed water and direct use from any modeled electricity-related footprint. Cooling categories can remain broad enough to protect security while still distinguishing dry, evaporative, liquid, and hybrid systems. Aggregation may protect an individual site, but it should not erase the basin, season, or utility carrying the risk. With that record, Oregon could compare promises with operation, whether storage reduced summer withdrawals, whether reuse returned the claimed volume, and whether peak demand stayed within assigned capacity. Without that follow-through, reporting becomes another stack of incompatible sustainability claims. The state can also preserve uncertainty instead of hiding it. Metered withdrawal can be reported as measured. Consumption based on an evaporation estimate can be labeled estimated. A company-supplied figure can remain company-supplied until a utility reconciles it. Reserved future capacity can sit beside actual use without being added to it. That approach would require the 41 million gallon difference to be flagged and reconciled rather than disappear inside a statewide total. Flagging the gap is not an accusation. It preserves uncertainty until the record explains it. Transparency would not settle every conflict. It would make the conflict specific enough to solve. Oregon needs to trace water from its source through cooling and discharge, then place that use in the relevant season, utility, and watershed. One giant number cannot do that work by itself. Hillsboro reported a modest share of a large municipal supply. The Dalles described funded infrastructure, while use quantities remained redacted. AWS supplied a statewide figure with 41 million gallons unexplained indivisible components. Hermiston and Prineville show that stored water and reserve capacity differ from last year's consumption. The March dialogue draft was not law, and the record reviewed here documents an ongoing advisory discussion. Its most useful contribution was stating the measurement problem plainly. Data centers do not all use water in the same way, and Oregon communities do not receive water from the same system. Comparable public reporting has to preserve those differences before the state draws a statewide conclusion. Until the figures are reconciled, Oregon has no verified public statewide total.